Jo Haig. I'm co-director of the Grantham Institute here at Imperial College, and it's a great pleasure to welcome you all to Martin's inaugural lecture. Martin came here last May. Previous to that, he'd been director of the Institute of Glaciology at Bristol, and before that, head of the School of Geosciences at Edinburgh University. But since he's been here, he has been the other co-director of the Grantham Institute. And we're having great fun. Oh, I shouldn't say that, actually, should I? The provost is here. I have to behave myself. And we're doing a very serious job, but having great fun as well, in moving the Grantham Institute into new areas. And I hope you'll all ask us about it and join our affiliate scheme and all the rest of it. But I shouldn't go on there at the moment. I'm meant to be talking about Martin. It's been a great pleasure working with him. And learning all about his interests in climate and the environment, but I haven't learned much about what he does in terms of the ice and the Antarctic. So I'm going to learn a lot today with you, I hope. And welcome, Martin, for your inaugural lecture.
Thank you. Thank you, Jo. Thank you. Well, it's a pleasure to speak to you, and thanks for turning up. It's a wet Monday evening, so my greatest respect to all of you for being here. Each of you will have some idea about Antarctica, all of you will, and some will have little knowledge, some will have an in-depth knowledge of it, but you'll all have some, and that knowledge will be derived from what you've learned in books you've read, in TV programs that you've seen, maybe in some research that you've done. And what I'm going to try and do this evening is try and understand how we've arrived at the state of knowledge that we've currently got about Antarctica. I can't cover everything, so I'm going to concentrate on the ice bit. You will all know there is ice in Antarctica, of course. I'm hoping that's true. And then a little bit about why it's changing and why we should care that it's changing as well. Okay. So this is Antarctica, and this is a satellite composite image of Antarctica, a satellite photograph, if you like, of it, and it'll be familiar to many of you. It's the highest continent on the planet. It's got enough ice in it that if all melted, sea levels go up by 60 meters or so globally. The ice is 3 or 4 kilometers thick in places. We know a lot about this continent now, but it wasn't always the case. In fact, you have to go back through history. It was people who first thought about the southern continent, Antarctica, were the Greeks, in fact, who thought that a southern continent, a southern landmass was needed to balance the Earth. And that affected the way that we thought about the world, and the map makers of the 16th, 17th and 18th centuries were heavily affected by the early Greek work, thinking that there was a southern landmass. This is somewhere around the latter part of the 16th century, detailing a massive landmass, of course, in the southern bit of the hemisphere. Now, see the rest of the world doesn't look too bad from a geographical perspective, but of course Antarctica looks nothing like that, but it persisted. And some of these maps were quite detailed, in fact, showing all sorts of rivers and mountains and topography and all sorts of stuff. There was imagination that was going into deriving these very early maps. But the one thing that links these independent maps together was the idea of a southern continent. This is the Chinese version as well. And you can see huge areas of land in actually what is relatively northerly latitude in the sort of middle part of the South Pacific over here. So what caused us to change that early idea? And what I'm trying to take you through in this lecture is ideas about Antarctica that get modified and changed through discovery. And the first person who really could stake a claim to having a seriously significant impact on how we appreciate the Antarctic continent was James Cook, Captain Cook, who sailed around the world 3 times famously, but it was the second voyage, the one in green over here, where he went into 71 degrees south, that's well within the Antarctic Circle, and may well, was pretty unlucky not to have spotted the Antarctic continent. In fact, may well have spotted the Antarctic continent unwittingly, but we'd never know about that. Sailed around in HMS Resolution on this second second voyage. But the thing about it is that he sailed in the Southern Ocean where the maps were saying there was land. And of course, in this amazing second voyage, they were able to sort of push the northern boundary of the Antarctic continent way south. The first person to see Antarctica the first people were Palmer, Bransfield and Smith, and they spotted the Antarctic Peninsula in 1820 on board a little boat called the Hero. And then very famously, James Clark Ross in two ships, Erebus and Terror, found the Ross Sea, Ross Ice Shelf, Ross Island, and an amazing voyage of discovery looking at the continent and mapping some of the coastline in a particular region of Antarctica. These two ships, Erebus and Terror, 2 years later, being with Franklin on the Northwest voyage to the Northwest Passage, sank, of course, and famously one of those ships has been recently discovered beneath the Arctic Ocean. The reason to set foot in Antarctica is disputed. And it's an interesting story because, and it kind of, I think this goes through all levels of science and not just science, other areas of life in general. The Norwegian, Carsten Borchgrevink, probably didn't pronounce that very well, lays claim to doing that because he definitely set foot in Antarctica in 1895. And this is a picture of him heroically getting off the boat and setting foot in Antarctica. They are first person. But what's not shown is a New Zealander who they picked up in the South Island, New Zealand, to do some general work called Alexander von Tonzelman, who also has a claim to be the first person to set foot in Antarctica. So Borchgrevink was the person who, it was his expedition, and it was sort of, he organised the finances and all those sort of things, and there we are. But people don't get off boats like this. There's always someone in front holding it. There always is. And that was Alexander von Tonzelman, who was standing on the boat steadying it so this heroic person could get off. And so you pay your money, you take your choice about who set foot in Antarctica. While all this stuff was going on, amazing discoveries were being found out about how we appreciate the world around us. It was a time of the Enlightenment, it was a time of discovery, it was a time of challenging orthodoxy, and no person was greater at doing that than Louis Agassiz here, who was the founder, we think, of modern glaciology. And he wasn't alone. William Buckland, a famous geologist, here a little sketch at the Ashmolean Museum in Oxford, demonstrating, quite frankly, a lot of things geological. And there's a lot of action going on in this particular diagram. There's ammonite over here, there's mammoths, tusks going over here, there's an ichthyosaur, quite another ammonite. So basically, there's every sort of specimen they could think about in the geological history is all pulled together. And because people were fascinated by the world around them and what geology was uncovering about that particular world, and people like William Buckland could do a public lecture, much like this, and I know it's the reason that this place is not completely packed and people outside is because it's pouring with rain. I'm sure that's the case. But William Buckland actually would be that way with him. There would be people standing outside because they couldn't get into his lectures. These are amazing times. And essentially what they did, these early people, Louis Agassiz and William Buckland, is they looked at topography and landscape like this. And the doctrine of the time was pretty much that this landscape was given to us by God. It was just, we were lucky, and we formed it this way, and we've received it. And what Agassiz and Buckland and some others showed was that actually you can explain the formation of this topography, this U-shaped valley in Austria, by the action of glaciers, and you can demonstrate that because the glaciers are actively eroding parts of the landscape right now. So you can look at these former glaciated areas, and you can look at actively glaciated areas, and you can make the links between them. And of course, it's not just Austria. You can go to North Wales, you can go to Lake District, Scotland, lots of places within the United Kingdom, and see classic glaciated landscape that has been carved out and formed by the action of glaciers. Not there now, of course. But why weren't they there? So the idea of glacial theory, the idea that we were once, parts of the world were covered with ice, started to provoke the obvious question, and that is why? Why did that happen? Because really what we're talking about is this 19th century understanding of climate change. That why was it cooler in the past? And there were two people responsible for understanding that. James Kroll on the left-hand side, who was a Glaswegian clerk, and Milutin Milankovic, who was a Serbian mathematician. And what they discovered through mathematics and clever calculations was that the Earth orbits around the Sun in a predictable way. But it's not a circular orbit. In fact, it changes subtly, like I said, in a predictable way. And you can calculate how much sun's radiation, solar radiation, is coming onto the planet at certain times in the past. And essentially, when there's not much solar radiation, that's when you're going to get ice ages. And when there is a lot of solar radiation, like we have at the moment, then you have what's called interglacials, between glaciations. And James Kroll was the first person to think about that. He got his calculations were right, but he wasn't necessarily a glaciologist. He thought that ice ages occurred as a consequence of having cold winters. You have cold winters, more snowfall, therefore the ice builds up. And that kind of seems sensible enough. But of course, that's not the case. The reason you have expanded glaciation is because you have cold summers, not cold winters. It's when you can't get rid of the snow. And that's when you start to build things up. And Milankovic made that slight adjustment to the calculations. But they both should be credited from that. The reason I put James Kroll up here is because he was a polymath. He had lots of different ideas about the world around us. And one thing that he was interested in was the Antarctic continent, having been discovered in the latter part of the 19th century by James Clark Ross and Palmer and others before him. And interestingly, he did some calculations on what he thought the ice thickness in Antarctica should be. And it ranged from somewhere between 3 or 4 kilometres and 10 kilometres or so, it's too thick, it's not that thick. But the amazing thing about James Kroll is he did all this before Axel von Tunzelmann, all the others, actually set foot in Antarctica. So this is the latter part of the 19th century, and things are changing. And they're changing quickly at this moment in time. Someone sets foot in Antarctica, and so enter what's referred to as the heroic age of Antarctic exploration. 7 years after the first person set foot in Antarctica, Captain Scott and Edward Wilson and Ernest Shackleton had their first serious expedition to try and get to the South Pole. And they didn't get very far. They got to 80 degrees south. They didn't get to the high elevation bit. They were just on the what's known as the barrier, the Ross Ice Shelf. It's a floating bit of ice. Got to 82 degrees south, 450 miles from the pole, and returned back. But they learned a lot of things in the process of doing that. Shackleton, on his own, was the next person to try, 1907 to 1909, the Nimrod expedition, and he did a wonderful thing. They tracked across the Ross Ice Shelf, a flat bit, and there's always been a difficulty because there's something called a ring of mountains called the Transantarctic Mountains, and you've got to get over the Transantarctic Mountains to get onto what they call the plateau, which is the big grounded ice sheet. And it was on the first expedition, they couldn't find a way to do it. The Scott, Wilson, and Shackleton expedition, they couldn't find a way. But Shackleton, in his second expedition, actually found a way. And it refers to this staircase suddenly becoming aware to him. And it was the Beardmore Glacier that they had discovered, in which they were able to work their way up. And he got very close to the pole, 97 miles of the pole. Worked out at that point that if they continued, they wouldn't have enough supplies to get back safely, and so they returned. But what they did was demonstrate an obvious and clear route from Ross Island, across the Ross Ice Shelf, up the Beardmore Glacier to the South Pole. And of course, that's what Captain Scott famously took advantage of just a few years later, made it to the pole, was beaten by 37 days or so by the Norwegians. Amundsen, you'll know all about this. And these famous photographs were taken. These are sort of haunting photographs that we know about. These 5 people at the South Pole, beaten by Roald Amundsen a few 30-odd days beforehand, and knowing that they had to try and get back. And those are haunting images. And we sort of left that. When people talk about the heroic age of exploration, that particular picture here often gets pushed about, but actually it wasn't always that way. This is Edward Wilson near the Beardmore Glacier, actually it doesn't look too bad, does it? And he's doing a drawing of the Beardmore Glacier, and it's a serene picture. It's a beautiful picture. And it's the case that anyone who's ever been to Antarctica, I've been 3 times, and there's many people here who have been many more times than I have, it's a world of contrasts. There are times when Antarctica is beautiful and still, and the sun is shining, and you get reflections from the snow, and frankly, you get sunburn, you get warm, you get heated up by the solar radiation. The air is very still, but not always like that. But this is a beautiful image, and that's available actually from the Scott Polar Research Institute in Cambridge. Shackleton, Scott, Amundsen, none of these people were scientists. Amundsen was an adventurer who wanted to go there to be the first person to do things, and probably so did Shackleton and Scott. But what Shackleton and Scott had were scientists as part of their team. And Douglas Mawson was a geologist, an Australian geologist, and he was part of the Nimrod expedition, 1907 to 1909. And while Shackleton didn't get to the geographic magnetic South Pole, Mawson did get to, or thereabouts, to the magnetic South Pole with a couple of colleagues. So he was a true adventurer. He then undertook his own Australasian Antarctic expedition a few years earlier. And by contrast to that beautiful, serene picture of Edward Wilson doing a sketch of the Beardmore Glacier, it's not always the case in Antarctica. And this is another famous picture of the camp that Douglas Mawson set up, a camp called Camp Denizen, which is frankly the windiest place on Earth. And they really had to set the camp up here because the ship that they were sailing in had enough coal to get back to South Island, New Zealand. I think it was a Hobart, I can't remember actually which it was. But they had to turn back at that point. So they had to basically get dumped on the coast, and there you are. And they set this camp up in the windiest place on Earth. The winds rip down the glacier, and they can reach up to 200 miles an hour. And so there's no photoshopping on this photograph. These are people trying to walk, and one of them's on his hands and knees, and the other one is bent over. There were some amazing pictures, and this is pretty much the worst place you can put a camp in Antarctica, but they did. But this was their mode of transport, and this is using huskies to get around on a ski. And this is Mertz and Ninnis, 2 of Mawson's companions, who both died on a trip. So there were good and bad news about using dogs to pull sledges. The good news is that they're very good at pulling sledges, and they also are a source of food as well, because you can kill a dog, and you can divide the meat up to the other dogs, and you can eat some of it yourself. Okay, so lovely, I know it's not very appetising, especially this time of the evening, but that's what you can do, and of course that's what Amundsen did as well. But famously, Scott and Shackleton, they didn't use dogs. They had dogs around, but they didn't like to use that sort of cruel idea of killing and feeding on them. So they used ponies, and ponies aren't good actually, and for a number of reasons. Their hooves get stuck in the snow. That's kind of obvious. They're good at pulling stuff, but once you've killed a pony, you can sort of eat it, but there's a lot of food left. So you've lost your pulling power, and you pretty much have to carry it, half a carcass, with you. So that's not good either. But this is a very good way, and this is how Amundsen famously got to the South Pole, by starting off with quite a lot of dogs and coming back with not many dogs, having ate them all. But the other bad news about dogs is be careful what you eat, right? Avoid the livers, right? Avoid the livers, because they contain too much vitamin A, and you'll get overdosed on vitamin A. And that is what happened to poor old Mertz on this particular voyage, that he was feeling a bit unwell, probably because he'd been eating too many dog livers to start with. And Mawson, who knew anything about this, of course, thought it would be a good idea to keep preferentially feeding him livers. So we look about it now, I know. But that's pretty much what happened, and he died. So Mawson somehow made it back. It's an amazing story. I mean, you know about Shackleton, you know about Scott, and you know about Amundsen, but check out Douglas Mawson. It's an amazing story, and a very famous geologist who spent a lot of his time at Adelaide University in Australia and did many great things. And Shackleton, of course, can't go unsaid, unspoken. An amazing journey that he had this idea that they would go from this part of Antarctica and they would track across the Antarctic. People had beaten him to the pole, so he wanted to do the first transcontinental expedition. So there was a ship going to wait for him over here somewhere. And of course, famously, his ship Endurance got stuck in the ice, and it drifted with the ice, and it sank, and they had to launch a couple of boats, the James Caird, to Elephant Island. Somehow they made it from Elephant Island to South Georgia. Somehow, a few of them, they were malnourished and in a dreadful state. Some of them, Shackleton included, made it over to South Georgia, and everyone was rescued. Again, another amazing heroic adventure. But not much science done on this particular voyage. But this is classically how people worked in Antarctica. If you don't have ponies and you don't have dogs, you do what's called man-hauling. And this is it. And it's hard, strenuous work. And it was like a lot of calculations going into man-hauling. It wasn't just load it up and try and pull it. There were strict calculations on exactly what you could carry and how much weight you could carry. And so the people were being looked after. But nonetheless, it looks terribly hard work, and indeed it is. And that's how the supplies got dragged up the Beardmore Glacier. The ponies were useless, they couldn't go up, so you had to man-haul it up. And of course, why should you try and do that? Why should you try and man-haul everything? And the Americans came up with a very interesting solution to that. And in an attempt for an innovation leap, the Americans decided, we don't swim in the ocean, right? We're trying to get from one continent to another, right? We cruise in a cruise liner. So why can't we do the same in Antarctica? Why can't we build a great big cruiser? We'll call it the snow cruiser, and we'll build it, and we'll go to Antarctica, and it will be like a boat, and it will allow us to simply sit back and drive ourselves across the continent. And so they built it, and this is it. It's a beautiful image. The snow cruiser, this is 1939. Here it comes. I love this bit. All these sort of old mobster mobiles and things trying to get past it. And there we go. And it's an amazing journey that it had from Chicago to Boston. It took several days. And because each of the local newspapers, they had to take the fire hydrants and things out because it was too wide. So they had to sort of knock them all off as this thing traversed through. Again, wonderful websites and stuff. If you just Google snow cruiser, it's an amazing thing. But it wasn't very good. Okay. But it's the innovation that's interesting, and it's the ideas that are interesting as well. 1928, first flight in Antarctica took place by Hubert Wilkins. And why should we not be flying in Antarctica? Remember, aircraft have been around 20 or so years since that point, and so it was a rapid innovation using aircraft in Antarctica. Famously, Richard E. Byrd, flew a year later. And this little stamp shows exactly what he did. He flew from the Little America camp all the way to South Pole. It took about 10 hours and back again on this sort of triple-engine plane, a single prop, a triple-engine plane that they have here. Lincoln Ellsworth, again, the first trans-Antarctic flight across the Ellsworth Mountains, and he named the mountain range the Ellsworth Mountains after his father, called it the Eternity Range, but we refer to them as the Ellsworth Mountains now. And these were pioneers. These are people who were flying aircraft which weren't particularly reliable, but they were taking them into unknown places and in the name of discovery. Of Antarctica, unexplored, penguins aren't there, it's unexplored. So quite a lot about the edges, but really nothing about the middle at all. And so this is only middle part of the last century, and we don't know a lot about it. And of course, the Second World War happened, but after that, 10 or so years after that, a remarkable episode took place in the understanding, frankly, of the whole planet, but in particular in the polar regions. It was the International Geophysical Year, or the third International Polar Year, and it took. The Second World War had taken place, and lots of scientific innovation had happened as a consequence. And this was an opportunity to put that technical knowledge to good use, to try and find out about the world around us. And there's a sort of an aim from the IPY in 1957-58, and it's as follows: to observe geophysical phenomena and to secure data from all parts of the world to conduct this effort in a coordinated basis by fields and in space and time so that results could be collated in a meaningful manner. Frankly, we could write that little mission statement right now. It's a wonderful and elegant way of describing how science should be done. And as part of the IPY, this was a overland traverse. Now, just a few years earlier than that, 20 years earlier than that, the snow cruiser was in town, but this was a different way of looking at it. It's using Caterpillar tracked vehicles in series with a lot of equipment. This is photographed by Charles Bentley, who was present as a PhD student at the time. And this is not at all dissimilar to a lot of traversing that goes on in Antarctica right now. So this rapid innovatory change had happened at a level that was extremely successful, and we still do lots of this type of work at the moment. There's a snow radar in front here, which is trying to look for crevasses, and so long as that doesn't show any crevasses, all these other things can go over it. This particular survey was trying to find how thick the Antarctic ice sheet was. We really didn't know. We didn't even know if there was a single continent or not. This is 1957-58, and so this particular traverse was over West Antarctica. And they used seismics. This is the same thing. This is the same snowcat and a seismic explosion that's going up. All right, so what do they find? Well, this is basically what you do. You sink a hole, borehole, 30, 40 meters, something like that, and another borehole nearby with some geophones, and you let off an explosion, as you've just seen, and the sound waves go down, and they bounce off interfaces between ice and water or bed or sediment or wherever it is, and you can record how long it takes for the sound waves to be emitted, reflected and received, and you know how fast sound travels through ice, and so you can work out the thickness of the ice. Pretty simple stuff. A borehole, 2 boreholes take about a day to do, and so this whole thing took about 1 day per data point. That's about it, 1 day per data point. But amazing data, because no one ever heard of anything before. And then Gordon Rubin, who was one of the proponents of seismics work in Antarctica, came up with an amazing thing. He died in 2004, in his obituary by David Drury in the Telegraph on 5th of October 2004, I'll read this quote. One of his most inspired decisions was to advance the charting of glacier and ice cap thickness by airborne radio echo sounding rather than explosions conducted at the surface. And so rather than using sound waves to propagate through the ice, you can use radio waves. And cold ice is virtually transparent to radio waves at very high frequencies, VHF, 60 megahertz, 100 megahertz, that type of frequency. And you can put a radar on an aircraft and point it downwards into the ice sheet, and you can record it every second or so. And in doing so, you can increase the rate of data acquisition instantly by somewhere around 5 orders of magnitude. It's a wonderful moment in science where our understanding of polar ice sheets was suddenly elevated to an obviously better position as a consequence of scientific technical innovation and its deployment. And there is Gordon Rubin. Not particularly good photo, but it's the best I can find of him. And this is what radio echo sounding data look like. So this has got this ice surface over there, and you've got bed over here. This is the bedrock, or whatever it is underneath, and a lot of internal lines here, and this is like strata within the ice. So ice is like a sedimentary rock, essentially, and you can work out this is around about 3 kilometers of ice. This is the middle of East Antarctica, this particular image. And what Gordon Rubin and his team did was discover about 40% of the entire continent within a decade, in the 1970s. An amazing achievement. And from that, this beautiful map of, you strip away the ice in Antarctica and look underneath it. In 1983, this is the geophysical folio that David Drury, who was a PhD student in the early times, but latterly director of British Antarctic Survey, formed a pretty good appreciation of what's underneath the ice in certain regions. But look, there's lots of regions over here where there's hardly any data at all. Okay, so go forward 18 years. And our knowledge has increased a little bit, but actually there were regions in 2001 where we still knew very, very little about. And so the 18 years since that compilation, 1983 to 2001, was this sort of data barren period in Antarctic exploration that we didn't advance our understanding of what's underneath the Antarctic ice sheet very much at all. And I'm afraid you have to excuse me, but this is where I fit into some of this discussion. So I've been very lucky to be involved in several programs, and there's one or two people who are here who have I have been very honoured to work with on some of these programs. The first I'd like to mention is a program that I was involved in with the Australians, the Americans, and the French called Icecap, and we flew a Basler BT-76, otherwise known as a DC-3, otherwise known as a Dakota. And the Dakotas are very old planes. They were, this particular plane was first registered, the fuselage, first registered in 1942 by the Canadian Air Force. And they were involved in D-Day. They dropped parachutists out of planes like this. And there were old Dakotas, you can see, with bullet holes in them. This one doesn't have any bullet holes in them. If you ever see a Dakota in the sky, it's got this throbbing engine. It's a cylinder-driven engine. These ones don't. These are turbo props now, and they've got a whiny noise. The aviation, avionics in here, completely different. It's a beautiful plane, and we were very lucky that we had a plane like this, and we put a radar system underneath it. And just like Gordon Rubin had done previously, and just like Admiral Byrd had done in 1929, we flew sorties from the edge of the continent into the middle and then back again, charting the conditions, the ice thickness, what's going on under the ice sheet across huge regions of East Antarctica, a little bit of West Antarctica as well. I've also been involved in a program working with the British Antarctic Survey, and this is a Twin Otter aircraft, another beautiful aircraft, with a radar system underneath it, and we flew a series of flight lines using a base within the ice sheet here in West Antarctica, trying to map out and understand what is causing the ice flow in this particular region here, what's underneath the ice, what is the geology like underneath that, whole series of scientific questions, and contributed to a better understanding of the Antarctic continent underneath the ice. So this again is 2001, and as a consequence of the data that I was involved in collecting, and many other data sets as well, I should add, we had a rapid change in our understanding of subglacial Antarctica from that early time to just last year. So this is it. I'm going to toggle between the two. You have to sort of put your eye in one place and take a look at what's going on. So first thing you can do is you can take a look at this region over here. This is the Institute ice stream, and you can see that the whole region suddenly becomes far more detailed in appreciation of what's going on. Take a look over this region over here. This is the Totten Glacier and the Aurora Subglacial Basin. Take a look at that point there, if you like, and you can see it's completely changed. Our appreciation of the topography in this region was pretty much as bad as the early map makers' appreciation of the Antarctic continent. Until you get a data, you think this particular region over here is like, what's that, 300 or 400 metres above sea level. And it turns out it's more like 800 metres below sea level just here. So, our whole appreciation of parts of the continent has changed. However, there are still bits where there's no data. Where you see a flat bit here in the data set, it doesn't mean that it's flat. Although I have to say, there was a paper that I was involved in, published today, and Catherine Rose is here. Catherine, your hand up. Very good paper that came out today, System Dynamics, showing there are flat bits in Antarctica, but you know they're flat bits because you have data proving there are flat bits. The reason this bit is flat and this bit is flat here is because there's no data. You can stand in two places in Antarctica, here and over here, and you can be 200 kilometres from a single point of data. We know far more about the surface of Mars than we do about the underside of the Antarctic ice sheet, even now, far more about that. And there are some places that we are completely ignorant over. I mention this because I'm very lucky to doing geophysical work in Antarctica. It takes a lot of planning. I mean, sort of putting a photograph of an airplane and saying we're just running it from a station and we're going out and coming back. It sounds easy, and of course it's lovely to talk about it in those terms, thinking about it afterwards. But the amount of planning and preparation that needs to go on ahead of those missions is really truly significant. But I have to say that I and colleagues from British Antarctic Survey and in China and in the States and Australia and India as well. We've just got money to do the necessary scoping study to work out how to acquire data in this particular region here. And this region here is called Princess Elizabeth Land, named after our Queen before she was Queen. There we are. These are called the poles of ignorance, 2 poles of ignorance, and we're hoping to fill one of them. In some parts of Antarctica, you've got the hills over here and hills, and then some bits you get amazing flat surfaces like this, and these are subglacial lakes. And there are lots of subglacial lakes in Antarctica, and I've been very fortunate to be involved in collating evidence of them, nearly 400, and they're widespread across the Antarctic continent, and they've been fascinating us for some time. Some of them are quite big. 4th largest lake on the planet, Lake Vostok, is 200 kilometers long, more than that actually, 40, 50 kilometers wide, 1,000 meters deep. It's underneath 4 kilometers of ice, and the water thickness is 1,000 meters. But there are many others as well. And they are interesting because they contain sedimentary records of ice and climate change underneath them. And because they're water, they contain probably life. It's a hypothesis that we have, and we've had some for some time. And we can test that hypothesis if we get into those lakes and sample them and recover the material, take them to laboratories and do analysis. And I was leading a project, which I'll come to shortly, about that. The current director of the Natural Environment Research Council, Duncan Wingham, gave me this map in 2005. And this is a satellite altimeter map. So this is showing you changes in the surface of the ice sheets in Antarctica. And usually it kind of looks a bit random like this. But on occasions you see you've got 3 green dots and a blue dot here. And that means that the ice surface is going down between 2 years. So that's over about 14, 15 months or so. And then anomalously, these red bits over here where the ice surface is actually going up. And we took a look at these and we thought this is rather unusual. And we looked at the signal to noise ratios and we concluded that it wasn't a noise problem and it actually was a signal. And it turns out what we'd identified was that a subglacial lake in one part of East Antarctica had an outburst. It lost a lot of water. And that water flowed 200 kilometers or so and into some other subglacial lakes, and they pushed up. So the ice surface went down as the water was lost, and the ice surface went up very locally as the water was input into these other subglacial lakes. Over 14 months, as this lake was losing water and these lakes were gaining water, there was a river that flowed under here. There's enough water in that river to equate to something like the flow of the River Thames in London. So in the middle of East Antarctica, for 14 months, underneath the ice, in the coldest bit of East Antarctica, the slowest flowing part of the ice sheet, where people had previously think there's really nothing underneath it at all of interest, there was a river flowing, much like the River Thames, connecting 2 subglacial lakes up. And so our appreciation of what's underneath the Antarctic ice sheet has changed as a consequence of those things. Now we know that there are many potential rivers underneath the Antarctic continent. There are many subglacial lakes that we know about, and some of these things are going to be connected up. And so the idea that it's a lifeless, static, frozen continent is being replaced by this idea that it's a dynamic, changing place underneath the ice in particular. So I was fortunate to lead a program trying to drill into one of these subglacial lakes, Lake Ellsworth, 2 years ago. And there are lots of news coverage on the BBC about this, and it's still all up there, so you can take a look. We started in December 2 years ago, and you will know, I think, because it was well broadcast, that we didn't manage to do the experiment that we wanted to do. And so we had problems with our drill, and so we had to call the mission off, which was terribly disappointing. I can't tell you how disappointing that was. But important things to learn from that whole experience as well, about how to do things, about what went wrong with the experiment, and also what went right with the experiment as well, and how to make it better in the future. And I should say that in 6 weeks' time, I and the team that I led and some American colleagues and some Russian colleagues and colleagues from all over parts of the world are going to gather together at the Royal Society's meeting place at Chichley Hall in Newport Pagnell. That sounds dreadful, but it's lovely. It's really lovely. And I'm sure Newport Pagnell was nice as well. I shouldn't diss Newport Pagnell. But it's like a manor house, and it's beautiful, and it's a retreat, and people can go there. And we will look at the the exploration of subglacial lakes. We'll look at the first results from various programs, and we'll look at the technological challenges that we've all encountered, and we'll plan the scientific exploration of subglacial Antarctica for the next 10 or 20 years. So it's a gathering together of international talent to look forwards, which we'll be very interested in. So the ice in Antarctica, it's not static. It flows, and it flows slowly, but actually, over a year, it can be quite quick, and it flows particularly fast in the edges, and up to several hundred meters per year it will flow, and these are called ice streams. And this is a satellite map of Antarctic ice sheet flow, and it shows a wonderful way in which the ice sheet flows very slowly in the middle and speeds up towards the edge and then gets quicker and quicker, and by the time it's at the margin where it's losing mass, it's actually going very quick indeed. Satellites have revolutionized our appreciation of the Antarctic continent, again, from being a static frozen place to being a dynamic place. We know what's underneath the ice now in places. We know the ice flows quickly, but how is it changing? And we really would have very little idea about how things are changing if it wasn't for satellite altimetry, the same type of altimetry which allowed us to understand that a subglacial lake lost some water and some other subglacial lakes gained some water, and we had a river like the River Thames for 14 or so months. We can look at other parts of the Antarctic ice sheet. This is a laser altimeter, so there's like a laser pointer like this, right? It's in a satellite, and it points down a little dot at the ice sheet surface, and then sometime later, call it a year or so later, it'll find another dot at the same place. And it'll be able to record the change in the thickness, the change in the elevation of the ice surface. And you can keep doing that, and you get this, over a while, this composite image of change. And the reds are where the ice thickness is going down, the blues are where the ice thickness is going up. And there's a couple of unusual things going on here. Clearly, this region, the Amazon Sea embayment, all around here, is a place where we are particularly concerned at the moment that the Antarctic ice sheet is losing mass. It's not melting as a consequence of surface melt, because Antarctica is, don't get me wrong, it is a cold place, right? And it's not really going to melt too much at the surface. But this is losing mass as a consequence of ocean warmth. And it's the ocean that may be getting underneath the ice and starting to cause that melting and the ice thickness to reduce as a consequence. And so we're particularly concerned about that. There are other bits of eastern Antarctica as well where we see similarly red bits where the ice is losing mass. So we are concerned in a few parts of Antarctica that the ice sheet is experiencing vulnerability to change, and is well evidenced here. You can see there's a bit over here which is blue, and that's the ice is going up. And this is an ice stream called, named by the British, Ice Stream C. Okay, so we've got ice stream A, B, C, D, and E and F, or something like that. Anyway, you can get the point. So we named those things. Lovely. And then they were renamed by some American colleagues, and it all got very confusing in the literature. I'm trying to understand what you got to, but I digress. The point I'm trying to make is that this is blue, so why is it going up? And that's because Gordon Rubin and his team worked out that this is very slow-flowing ice right now. They kind of worked that out. But it's very flat on the ice surface, but underneath that, there are evidences of crevasses. Where the ice flows quickly, you get crevassing. But what they saw was flat surface, but crevasses underneath it. And they calculated it took about 150 years of snow accumulation to get where we are today. And so this is an area of the Antarctic ice sheet that was flowing very quickly 150 years ago and then suddenly stopped. And as a consequence of stopping, it's now, ice thickness is going up. Because it's not being lost and pushed out, the ice is simply getting thicker and thicker. And so that happens as well. It's not just about oceans warming and eroding and melting the ice. It's about the way that the ice flows as well. So we have a complicated engaged system between the mechanics and dynamics of ice, the subglacial conditions, the ocean temperature, and the climate, of course, all around us, which is affecting some of those things. We had no idea about this 20 years ago. But our understanding of Antarctica results to the IceSat laser altimeter as well, indicating that it's not just one instrument. This is not just like an artifact of laser altimetry. It just gives you that result. You can do a completely different technique and come up with the same answer. So it's a robust thing, and Antarctica is changing. Okay, so Westminster Abbey. Why have I got a picture of Westminster Abbey? That's because what we're seeing here are flying buttresses, a great Gothic invention. So you can have a massive stone wall and building, but if you didn't have these flying buttresses, then the whole thing might just sort of fall over. And so these are buttresses which act to support the building. Beautiful. And ice sheets have similar things as well, and they're called floating ice shelves. So the ice here is grounded on bed 2 or 3 or 4 kilometres thick, but all around it are a series of floating ice shelves. This is not sea ice like you get in the Arctic, which is a metre or 2 thick. This is an ice shelf. It can be 2, 3, 400 metres, maybe a kilometre thick at this point, 300 metres thick or so at the edge. These are thick bodies of ice. This is what Captain Scott had to walk across the Ross Ice Shelf, up the Beardmore Glacier to the pole. Amundsen took a different route, probably more successful in that different route. But if you take away these ice shelves, then you take away potentially the mechanical support of the ground in ice. And so we're particularly worried about the conditions of these ice shelves around Antarctica. And in particular, what the British Antarctic Survey have done on the Antarctic Peninsula points to several of these ice shelves being vulnerable to ocean and climate change. In particular, and famously, the Larsen A ice shelf in 1995 got broken up very quickly, and of course Larsen B in 2002 lost a lot of its mass within a few months. I mean, it basically exploded internally. I mean, the whole thing just completely carved up. And glaciers that were flowing into this suddenly increased their speed as a consequence of losing that buttressing support. So we're particularly worried about these ice shelves in other regions. Why particularly are we interested here? Well, this is a map of global temperature change, 2005 to 2009, relative to that period 30 years or so before it. And it's a map that you'll see a lot of in terms of global climate warming, and it's, again, a real thing. But interestingly, it's the polar regions that get what's called amplification, get enhanced warming in the polar regions. And the bit of Antarctica that experiences polar amplification is the Antarctic Peninsula. Well, here's the concern, because if the type of amplification you're getting in the Arctic is ever repeated in the Antarctic, then those ice shelves are going to be in jeopardy, and the ice sheet, the grounded ice sheet, may well respond as a consequence of that. Oh, okay, conjecture, hypothesis, you might say. So has it changed in the past? And you know, as a geologist, we can look into the past and get the amount of carbon dioxide in the atmosphere has declined. There are episodes going up and down, of course, but the general trend is cooling to where we are right now. But here we go, because if we keep putting carbon dioxide into the atmosphere, and the relationship between carbon dioxide and air temperature is, as we believe the ice cores tell us, then we don't have to go very much further in time, 100 or 200 or so years, before we're going to get a level of carbon dioxide and therefore potential amount of warming that we haven't seen since the dinosaurs were around. And so the implications for many things on our planet, of course, are significant. But for Antarctica, we're talking at a time where there was no Antarctic ice sheets before when the dinosaurs became extinct. And so, you know, we are entering a world, a carbon dioxide world, which is not new to the world. 1,000 parts per mil was around, you know, more than double what it is at the moment. But it has happened in the past, but the temperature was much warmer. And if that's the case, we'll live in a world without ice. Lose most of the West Antarctic ice sheet as a consequence of the warming at around about that time. So it is changing, and it has changed, and we know a lot about the Antarctic ice sheet. But why should we care about that? Why should we care? Well, is there anyone from the Foreign and Commonwealth Office here? Thank goodness for that. Right. If they were here, they would say it's because it's British. That's why we care about it. It's British. And it's true, that's what they say. And it's also true that a bit of it is British, the Antarctic Peninsula, and a bit of British claimed territory. The Antarctic Treaty works that the existing claims in Antarctica, and there are 7 of them, are in abeyance, but the ones that people that have claims can keep those claims, and they can't be challenged or changed or what have you. And so, you know, we can put the British, the Union Jack, and it's British, and so we should care about it because it's us. We should also care about it because if you get rid of all the ice, then this is what Britain turns out like. And, well, we're in trouble in London, actually, aren't we, looking at this? But should we be concerned about that eventuality? Well, it will take some time to do that. And we'll come on to rates of change in a minute. But just call it a metre of change. And there was a wonderful project called Ice to Sea that the British Antarctic Survey led and many European partners. And they had this understanding that you can take those sort of extreme events, 60 metres of sea level rise, and the UK gets completely changed. But, you know, from a policy perspective and trying to understand what it really means to us, that's not going to happen over the next 100 or so years. But what we understand about the last ice age, when there was lots of ice around, that it's entirely plausible and feasible for a metre or so of sea level change to happen over that type of timescale. And if that was the case, then there would be bits of Britain that were affected, but many parts of continental Europe, of course, that would be affected by that as well. So it's a real thing. Let's look at sea level change, measured sea level change. And very interesting recent survey, just a few weeks ago, modified this graph a little bit. Basically what it's showing is that the British Navy did a wonderful thing for us, right? They put ports and infrastructure around many parts of the world, and they measured the tides, right, religiously, and with great records. And so we're able to determine the height of the tides through many years of British naval presence. And those measurements got better and more precise. And then, of course, we have, in the age of satellites, you know, many more information, much more information. What it shows you is that sea level from 1870 or so has been going up by 30 or so centimetres or so, at a rate of around about 0.8 millimetres per year to 2 millimetres per year to now 3.2. This has been revised down recently, just 2 or 3 weeks ago. This figure's been revised down, and that doesn't mean that don't worry about it because it's less sea level change. The amount of sea level change hasn't happened at all, but what it means is the rate of increase from 3.2 to 2 is actually greater. It's more like 1.2 millimetres to 3.2 millimetres. That means things are changing more rapidly than we had appreciated previously. And what does it mean for places like Bangladesh? So, I mean, the last ice age, sea level was 120 metres lower than it is right now, as a consequence of ice on North America and other such places. And the rate of sea level rise was of the order of 1.2 metres per century for 10,000 or so years. There were times where it was a little bit more, 3 metres or so, times a bit less, but of that order. So that's how the cryosphere can change. That's how the ice on our planet can react when it warms up. Ocean warming, atmosphere, in places like Bangladesh, and so and other low-lying areas of the planet. And so it's a concern to us that we look at the cryosphere in a way that we want to find out more about it. But there's a reason we want to find out more about it as well, because it may well, through its changes, have impact in other places. You might say Antarctica is a long way away, and so far we should be looking at Greenland more than Antarctica, because it's much closer. Well, the thing about Antarctica is that it's such a massive ice mass. It's so large that it has its own gravitational, well, all masses have gravitational attraction, but it's particularly large. It has a significant gravitational attraction. And so curiously, when the sea level is artificially high around Antarctica itself, and curiously, if the Antarctic ice sheet loses mass, sea level around Antarctica actually goes down a bit, weirdly. But we are a long way from Antarctica, and so we don't have that gravitational attraction. We don't observe that too much. And so what we get in the Northern Hemisphere is the most significant part of that sea level change. So even though Antarctica is a long way away, other part of the planet, the changes going on in Antarctica will be felt the greatest in the Northern Hemisphere and in places like Great Britain. So we need to be concerned about it for scientific reasons, for curiosity reasons, because we want to find out about stuff, but also for humanitarian and societal reasons as well. Thank you very much. Thank you.
Are you go first. Okay.
Okay. Well, I'm deeply honoured to be able to give the vote of thanks for Martin, who I've known for many years, actually. And as you can see, Martin has shown you just how awesome Antarctica is. And I think the word awesome is actually invented for Antarctica, because it really is. And as Martin explained, we've got this big continent of ice. It's a bit like a big freezer cabinet at the bottom of the world, and it affects you and me. So although there's nice pictures of it, and it's a very long way away, and it's a huge continent, it does actually affect us as we're sitting here, because it affects how the ocean currents flow, it affects our climate, it affects our atmosphere, and it affects the sea level, as Martin has said. So it's a long way away, but it is actually influencing our climate now. And there is a scary feeling among some scientists now that actually, as Martin said, some of those ice sheets are melting, particularly because the oceans have warmed up and they're melting the ice shelves that are holding the ice back on Antarctica. And there's some of us who think that we're already in a position where that has started and isn't going to stop, and we're going to lose some of that ice in Antarctica. Antarctica is a big place. It's remote, it's harsh, it's cold, like Martin has shown, and it really demands big, challenging projects and big, challenging science. And Martin has been one of those people who've really challenged Antarctica and the science of Antarctica, and has really led some of the really big projects that go on in Antarctica. And the other thing that Martin hasn't really mentioned is that Antarctica is really a very special place, because it's called the continent for science. And although Martin mentioned about sort of the British claim, actually nobody recognises that anymore, except for the Foreign and Commonwealth Office. And Antarctica really is a continent where there's something like 52 nations doing science there, peacefully. We're all friends when we get down there, and we all work together. And there is a group, a committee called the Scientific Committee for Antarctic Research, SCAR, that brings all the scientists together who work on Antarctica, who protect the environment according to the Antarctic Treaty that they all sign. And the SCAR group really helps develop the future science of Antarctica. And just recently, there has been a really impressive exercise that Martin and some of my colleagues in the room have taken part in to do a horizon scanning exercise for the future of Antarctic science. So what will Antarctic science look like in the next 20 or so years? There are some really big questions to answer. You can see, Martin said, if those ice sheets melt, we are going to be inundated by higher sea levels. Our climate is going to be affected, even though we're living so far away. And in SCAR, Martin has provided a real leadership role that he's been very modest and not mentioned. And in recognition of all his work in Antarctica and that leadership role in SCAR, Martin was awarded a very prestigious prize called the Martha Muse Prize, which is given annually to mid-career scientists, and it's highly, highly competitive. And Martin won it last year. So well done to Martin for that. So you can see that Martin really is one of the great leaders for Antarctic science. You've seen that today. He's running big projects. He's leading some of the big future science projects in Antarctica. And I'm sure he'll go on to lead the Grantham Institute in exactly the same kind of way. So I'm sure you'd like to thank Martin for his talk. And would you join me then, please, in thanking him for his talk?
Standing between 150 people and a glass of wine is never a good place to be, so I'm going to be quite brief. One of the things, well, my name's Mark Brandon. I'm at the Open University. I was a PhD student at the same time as Martin. So what I get to do is talk about a couple of things. Firstly, your generosity. If you're not a polar person and you listen to that talk, you probably wouldn't, well, it would be very difficult to pick out Martin's contribution because he buried it so deeply. But there are areas of science there that just wouldn't have developed in the same way without Martin. So, about Martin's generosity determination. Martin was generous and persuasive enough to persuade me at Scott Polar to join the five-a-side football team. So every week I would go out there and play. And that was great until one of our colleagues who wasn't as generous in spirit tackled me quite badly, and I broke my wrist and ankle at the same time. But Martin was generous. He said, I'll take you to the hospital. But he was determined enough to make me sit on the sideline until the game finished. So he took me to the hospital, dropped me off. Then while I was on crutches, he took me into the darkroom because I was very interested in photography at the time, black and white photography. Martin was doing computer modelling, so he wasn't really interested in that sort of thing. And he said, I want you to show me how to develop pictures. Okay, what have you got? Thinking it was going to be some nice pictures of Cambridge, flying buttresses perhaps, that sort of thing. But it wasn't. It was these really boring white plots with these sorts of stripes across them. Oh, what the hell are they? Anyway, I take him down in the dark room, on my crutches, standing there for 6 hours in the summer. I show him how to do it. Of course, 6 months later, the paper about Lake Vostok and the first mapping of Lake Vostok came out. And so the stuff that I'd contributed to, he used that and mapped out Lake Vostok. And the slide that he put up was quite throwaway. He said, there are now 400 lakes in Antarctica. Well, in 1985, wasn't it? How many were there? And that sort of comes from the sort of work that Martin's done. Now, I was the lead science advisor on Frozen Planet, and I tried really hard to get the BBC to look at under ice lakes. I thought, this is the thing you want to be, you want to be pushing this. But it was too risky because they weren't really sure about it. They thought it was too much frontier science, and they wanted to be on more solid ground. But I think now, if we would come to the program now, maybe they would have think differently. So back onto the determination. Martin, from Lake Vostok, the view of now how we understand subglacial hydrography has completely changed. Martin talked about Lake Ellsworth. Lake Ellsworth was a huge British project. Martin had the vision and drive to get that forward, the determination, the persuasion, the ability to make UK Natural Environment Research Council think in a different way about funding and a way to do this and to bring this whole team together and get people to commit to it. And the generosity of him comes through in that he didn't really mention himself and all his contributions to all this. But there was an article on the BBC website, which you probably missed quite recently, which mentioned Lake Ellsworth. And it was about British glorious failures. Now,
Yeah, I missed that one.
right, now the 3 failures on the page. I work at the Open University, and of course we did the Beagle. And the Beagle was a glorious failure. Of course, it wasn't to my university, and the article was when they found the Beagle on Mars. And they said, look, it's there, and it turns out that it was perhaps just one small engineering issue that stopped it. Other professors in this university, in Imperial, worked on Beagle. The second thing that was in this article was Captain Scott's expedition as being a glorious failure. And the third one was Martin's, Lake Ellsworth. And in it, it quotes Martin as saying, I hope it doesn't turn out like Beagle. But you see, the reason for raising that is there are 3 points there. The Beagle, Scott's expedition, and Martin's. And I think depending on where you sit, none of those were failures. The equipment and the development that went into Beagle is now standard equipment in British nuclear submarines for detecting air quality and things like that. If you look at Scott's expedition, Martin raised a point that it was about science. We didn't know about fossils from the interior of Antarctica for 50 years, except for the ones that Scott brought back in 1912. And it's the same with Lake Ellsworth. It's very cheap and easy to view it as a failure, even a glorious failure. But it was a massive step forward, and the direct logistical things that Britain has developed from Lake Ellsworth have gone forward to some of the biggest projects which are working in Antarctica now, led by the British, in the Ice Sheet Stability Programme, which you'll hear about in a few years where that comes out. So to finish up, again, in generosity of spirit and the ideas, the sub-ice topography and lakes underneath ice, 30 years ago, people didn't really think about it, but of course now it's the latest thing because there was another article which highlights on the BBC website about Ellsworth in the last couple of months, and that was about Europa. And Europa, this ice planet, or icy moon, is there going to be life underneath it? And the same ideas and the same sorts of physics and things that Martin has been researching, they're going to take forward to Europa. And actually, Martin wrote about that for the American equivalent of New Scientist, American Scientist, back in the early 90s. You've probably forgotten about it. So I'll finish there and ask you to clap once again and say thank you to Martin for a fantastic talk. Well done, sir.
Thank you also. Thanks very much. Thank you. Later, and we can get a drink now. I believe we go upstairs and get a drink. See you there. Thank you.